Okay, now let's do an example problem actually using our Bernoulli's equations that are built out of conservation momentum. And I want you to know this is actually a very practical problem because it's something we'd actually do in real life if you're doing lots of experiments. So let's get to it. We have a pitot tube and it's being used to measure the velocity of air flowing through a duct, or a wind tunnel, or over a wing. And the manometer shows a difference in head of 5 centimeters of water. Now, a manometer is just a pressure measurement device. It uses a liquid, in this case water, and it has like a U shape. When air presses down on one side, the liquid moves up on the other side. And you can tell how hard it's pressing by the change in height. Then it tells us that if the density of air and water are 1.13 kilograms per meter cubed and 1,000 kilograms per meter cubed, we want to find the velocity of air. Now, to start off here, you need to know that pitot probes measure the difference between moving and stationary air. Moving, we're talking about static because we're going to say that it is not accelerating, so statics, that whole sum of the force is equal to 0 equation. That'd be our static pressure. And if it's stationary, that is stagnant, so that's our stagnation pressure. So it's measuring the difference between our static and stagnation pressures. That's important. We're going to need to know that for later on. Now, let's go ahead and pull out Bernoulli's and see how it helps us. So, same as last time, our pressure plus 1/2 rho V1 squared is equal to our pressure plus 1/2 rho V2 squared. Now, from what we learned about our pitot probes, one of these velocities is going to be 0 because it's stagnant, it's not moving. And I can choose either one because it doesn't have like a diagram or anything. I'm going to choose V2 and make it that 0. So I can then rearrange this and I say, okay, my change in pressure is equal to 1/2 rho V1 squared. Or my velocity would be equal to the square root of this guy. Now I know the density of air, so I'm good there, but I don't know that change in pressure. So how do I get that? Well, I get that from my manometer. So my manometer is going to tell me that difference in pressure. It's all based on the height of the water. That height of water, its hydrostatic pressure is actually the same as the difference in pressure between my static and stagnation points. So I can plug that in here. So hydrostatic pressure is simply density gravity times height. And so my change in pressure is going to be equal to 490.5 pascals. That's the density of water times gravity times its height. And notice I did change it to meters because everything else was in meters. So 5 centimeters is 5 over 100 meters. So if I have my pressure in pascals, then I can probably plug that into my equation and get a velocity. And so I do. And note here that I'm using the density for air because I'm finding the velocity of the air here. And it comes out to be 29.46 meters per second. So this is a very practical problem. You would be using this a lot. And you can actually build one of these yourself. Like you can build your own manometer and you can see from it how fast air is moving or the change in velocity for air as it moves through your wind tunnel. So try it out. Hopefully this helps you, and I'll see you all next time. Bye-bye.